All right. Yeah. So the kinds of systems that I'm going to be talking about are chaotic systems. So in dynamics, and generally in dynamics, what we're interested in are the long-term behaviors of systems. Typically, you sort of have some equilibrium or Lipit cycle that you would like to study and maybe study the convergence towards. But for chaotic systems, you don't really have that because you're just kind of bouncing around in the tractor forever. And so the kinds of objects that you really want to study are ergodic theoretic objects, really. The most, I guess, important one is a so-called physical measure. So in many situations, it's actually an absolutely continuous invariant measure. And this really tells you if you run your system for a very long time and take some sort of average, for example, of a function, this sort of Birkhoff average will converge for almost any initial condition to an average with respect to this measure rho. And you can see this in this diagram here. At some level, what that tells you is that you, sorry, Brain, the kind of empirical measure of your time series will converge weakly to this invariant measure. If you're looking at these Birkhoff averages and you want to consider the sort of the second order correction, it's actually a central limit theorem kind of idea where you have a sort of 1 on n in the variance times a constant here, which kind of behaves like a variance in a normal sort of independent random variables, but it is defined in various ways using, say, a Green-Kubo relation. And yeah, there are many other things you might want to study, but these are the two that we're going to focus on in this talk. I suppose the asim being like the very important thing that people like to really care about, and the diffusion coefficient being something a little bit more complicated. In general, a big problem with chaotic systems, just as a field, is that a lot of more complicated systems are really not too complex to really be able to do anything particularly rigorous with. So when we like to be more theoretical, we generally have to think about simpler cases, subclasses of systems, and a very standard one, which I'll be talking about in this talk, are those of so-called full branch uniformly expanding maps. They look something a bit like what's on the right here. You can see my cursor, right? Yeah, cool. Right.
Yeah, yeah, we can.
Yeah, so where they're kind of essentially many to one, as if you draw them as a graph like this, so they're maps of they're discrete time dynamical systems that are maps of the interval, and they're kind of many to one. These are just, I mean, they usually don't represent very much in particular, but they are a nice sort of illustrative model class that you can sort of show that certain properties of chaotic systems hold. If you want, there's also various examples that are actually of their own theoretical interest. So the Gauss map, which sort of gives you the remainders of sort of successive iterates of continued fractions, is a good example of this. So that's what you have on the right-hand side, and it is an uniformly expanding full branch map under a sort of slight transformation. And so there are many theoretical problems, and you can imagine in number theory being one place where they crop up, where you can answer these kinds of, where there are theoretical problems that can be answered using rigorous numerics on these systems. A sort of concrete example of that is the dimensionality of, sort of questions about Lagrangian Markov spectra in Diophantine approximation. And recently there was a paper, semi-recently maybe, about essentially showing sort of the set difference between these two things, which I don't want to talk about too much, but it was sort of reasonably fat. So there is, there are a bunch of sort of actual theoretical questions that you can answer, and then there's sort of questions about like, well, what kinds of chaotic dynamics can you get, which are also of interest. And there are a couple of different methods that people like to use to study these things. One of them is the idea of dynamical zeta functions. Also uses the sort of theoretical techniques of dynamical zeta functions, which involve sort of probing, like computing large amounts of periodic orbits and using that to reconstruct these statistics. So people like Mark Pollicott and Oliver Jenkinson and a bunch of other Brits tend to do this. It's limited, and it works really quite well, and you can get some very good estimates. The problem is that it is usually only practical if you have a few branches of your maps. So for example, this is a terrible one because it has an infinite number of branches, and you have lots and lots of periodic points. It also assumes that you also kind of need your maps to be analytic, which most maps are, so that's fine. But if you have something that's not analytic, you might want to be able to do something with it. So the other kind of method that people like to use is Ulan's method, which is a very sort of flexible, generalizable method that a lot of people use it because it is so general, but in a rigorous setting, sort of people like Stefano Galatolo and Isaiah, who's here, and so on, and their collaborators sort of have done a bunch of work on this. It essentially involves taking a phase space and sort of just chopping it up into boxes and discretizing it like that, sort of kind of discretizing a phase space. It is a very low order method because you're sort of essentially assuming projecting onto piecewise constant functions. And so generally the kinds of rigorous results you get out of this have, you know, maybe like you might get a couple of digits, which probably for many applications is fine, but perhaps also for more complex applications, perhaps leaves something to be desired. So really the goal, what we'd like to have are maps that are both quite powerful, but also quite broadly applicable. And in particular, the method that I'll be talking to you about today, which is I suppose a Chebyshev Galerkin method for these transfer operators, does both. And in fact, it performs better than the dynamical zeta functions. And so I suppose what we'll do in this talk is describe what a transfer operator is and what it does, the sort of, I guess, the way the method works, say something about its convergence and how you can apply that in a validated sort of context, and show it with some results. And then maybe if we have a little bit of time at the end, I'll show an example of where you can apply this as a kind of building block in doing rigorous numerics for more complicated systems about which we know a lot less. Essentially, which will be non-uniformly expanding maps. I guess to be a bit more explicit about what maps we're going to consider. So these uniformly expanding maps of the interval, these are maps of the interval with a countable partition of sets, which we'll call these O's, although the O's won't turn up again. But they're a countable partition of sets on which, if you just restrict to this, you have a one-to-one, like these maps are one-to-one. They have inverses VI. If we want to do nice numerics, we need some nice regularity conditions to give ourselves compactness and whatever. The regularity condition we're going to use is the sort of bound on the so-called distortion, which is just the log of the derivative of these inverses, and either their derivatives are bounded, or they extend to the complex plane and have their in some complex set, these distortions are bounded. And the sets we're going to use are going to be Burns. I mean, doesn't really matter, but when it comes down to computing the explicit bounds, the sets we're going to use are the so-called Bernstein ellipses, which are essentially ellipses. I mean, if your domain is -1 to 1, they are ellipses with certain semi-minor and semi-major axes, depending on this parameter delta, which will tell us how fast they, sort of the kind of associated rates of convergence that we'll get. And this comes out of the fact that we're using a Chebyshev basis, which has got connections via cos transformation to Fourier series. There's a technical requirement on these domains, which is not very interesting or important, and a so-called C-expansion condition, which is essentially the same as a uniform expansion condition, which says that your derivative has to be bounded away from 1, so you get stretching, which is important. Which is, I mean, like the sort of basic idea of chaotic system, you need stretching, you need folding, and this is the stretching component. But because of this, again, because of this cos transformation, which we will find out more about later, we need to actually make it so that the derivative of this conjugacy is bounded strictly away from 1 by this parameter gamma hat, and that's usually satisfied by most maps that are uniformly expanding. So, which is where f dash is bigger than 1. Yeah, so those are the maps. The standard map used in this class that people like to use in numerics is the so-called Lanford map. It looks a bit like this. It's really just, it's at some level just a perturbation of the simple doubling map, which is 2x mod 1. Which we can actually calculate a lot explicitly. It's like one of the only maps we can say very much explicitly about, but obviously if we perturb it a bit, it's not going to do that. Yeah, it's just a nice map. For comparison, I've been use this to test things, but you could use any other map really. These methods are quite general. So to study these maps, we're going to use the transfer operator. The idea of a transfer operator is that it takes sign measure densities. So you have some measure and you push it forward under the action of the flow, and you see what the density is after that. And it applies on some Banach space, usually of smooth functions, to get nice functional analytic properties. Mathematically, you can sort of write it as the adjoint of function composition. But it has, I mean, coming out of this, it has this kind of explicit formula, which you can actually evaluate pointwise very easily, provided you don't have too many branches, or provided you have a finite number of branches, or you can sort of easily evaluate an infinite sum, which is basically just a composition with the inverse map here. So it's summing over the pre-images of the map. So all these different branches, and then times the Jacobian. There are, for various other purposes, you can write sort of slightly different transfer operators, which more I guess generalized transfer operators, which don't necessarily have this measure density pushing forward quantity, but they will let you do other things, which we're not going to talk about in this talk, but it is like this. Some of the ideas here can very easily just be applied to those. Yes, the nice thing about the transfer operator is that it's quasi-compact on a range of, for these maps, like pretty much any reasonable Banach space of a sufficient degree of regularity, or like of not too much regularity. If it's, not a perfectly, it's not an analytic map, you won't get it to work on an analytic space, but you might get it to work on some highly differentiable space. And provided you choose the right Banach space, you will get a you will get an eigenvalue at 1, and then that eigenvalue will be isolated because you'll have some essential spectrum and just some point spectrum bounded off the unit disk. So what's relevant for us really is that just you have this isolated eigenvalue at 1. We will use, which is where we'll find the invariant measure and various other things. The Banach space we're going to use in this talk is BV, which is a space of bounded functions of variation. So the norm is just, there's the total variation, which is, I guess, the sum of the amount it goes up plus the sum plus the amount it goes down, plus the infinity norm. This is a nice space in some level, because if you multiply two functions in it together, you get the norm of the product is bounded by the product of the norms. It's not like, to be honest, if I were, it's perhaps not the most natural norm for the Chebyshev spaces. We should really be using Hilbert space, but it's what we've been going with. So, and it does actually work very well for things like Ullm's method. So yes, but basically the idea is you have a function space that's a Banach algebra. The quantities, when it comes to like expressing quantities of interest, as I said, they really depend on the resolvent data at the eigenvalue 1. This invariant measure is kind of, as to be expected, the one eigenvalue, and we'll say one eigenfunction of this because it's invariant under the action. Like it's a measure density, and you push it forward and it stays invariant. And it's normalized so that the total integral, which we'll use using this little script letter, I think it's a script letter S actually, but looks like an I, is normalized to equal 1. So that's the problem. It satisfies the diffusion coefficient problem, satisfies something a bit more complicated where it's looking at lag correlations. You don't have to worry about the formula. It's not very important, but it looks a bit like this. It's got, what is important is it has this infinite sum over iterates of the transfer operator. So this kind of, if you think of the adjoint, it's sort of composing with f to the power of I, and that's a kind of lag vibe. I think what's important here is that there's really no explicit solutions to either of these problems for almost any map. This is kind of why we need to do numerics. Yeah, so that's, but you can solve these things using the transfer operator. That's what's really important. Okay, so the kind of, I guess, way we're going to approximate these operators, which are obviously infinite dimensional, so we can't get them exactly, are using a basis of Chebyshev polynomials. Chebyshev series are probably things, I mean, I'm sure you've all seen them, but they're essentially, well, you can sort of, they have this kind of form here. They are actually polynomials, although they have this trigonometric definition. You can see that they have this relationship to Fourier series by a transformation on the, I guess, on the domain, where you say x is equal to, or theta is equal to cos inverse x, and you just get a cos function. Coming out of that, you have this nice orthogonality relation, which is, I guess, that they're all orthogonal with respect to this weight. They're not orthonormal. There's this little tk inverse times pi, which has this expression here. I mean, it's just the same with, it's the same as with causes. It's not very important, but it'll turn up in the equations. And essentially, yeah, they just look, they're just wiggly. They tend to wiggle more towards, like, they're more oscillatory towards the edges than towards the middle. But they're all kind of bounded between -1 and 1, a bit like a cos function with a domain transformation. And the reason we're going to use them is because they're probably the best function approximation basis in for intervals in the same way that Fourier series are for periodic intervals. And so they do actually, if you want to approximate a function with them, so say some psi and write it as a sum of Chebyshev coefficients. Well, okay, it's easy. You can, by orthogonality, you can figure out what the Chebyshev coefficients are. But we have this really nice fact that these coefficients will decay at what we'll call a spectral convergence rate, which is just, you know, polynomial if it's if your function that you're approximating is differentiable, and exponential if your function is complex, and complex on a Bernstein ellipse. So it's very natural to think about these things. And you can see epsilon minus delta k for this e to the delta Bernstein ellipse. Yeah, so we'll see sk written just as shorthand for this. Mostly we're going to focus on the analytic case though. So we can ask, well, what happens if we try and write the transfer operator, or like think about the transfer operator as acting on these Chebyshev coefficients, or acting on functions in terms of Chebyshev coefficients. So if we just, I mean, you know, you can associate a function with the vector of its Chebyshev coefficients, which you can pull out like that, and vice versa and so on. What this essentially runs down to is thinking about LJK as like an operator on vectors. So it's kind of like an infinite matrix. And the coefficients in this infinite matrix have this kind of expression here. And well, okay, I guess that's like an integral against some things. What is that, like, how can we understand that? Intuitively, we can see that if we apply, I guess, we can see that by thinking of these coefficients JK as the Chebyshev coefficients of the transfer operator applied to a basis function tk. And okay, so what happens if we do that? Well, as the transfer operator is just a sort of composition with these VIs, which are contractions. So they, I mean, if you compose with the contraction, a sort of wiggly function of the contraction, you're kind of stretching it out times a smooth Jacobian. And so we think about L and we have this wiggly function of a given frequency. We're stretching it out and then multiplying it by a smooth, like a sort of not oscillatory function. And well, we're doing the same thing, but for the other half of this L, and we're going to get something that is still wiggly, but is not as is of a low, like tends to be of a lower frequency. So we would expect, therefore, that if we have that the sort of components, like the sort of coefficients of high order Chebyshev polynomials in this function here are going to be very small. Whereas if they're, it's a lower order might be quite large. But for the higher ones, they're going to be small. And we can prove this using oscillatory integral techniques on this relation here. And so what this actually looks like, if we sort of kind of, compute a matrix of these coefficients and then, plug them into log abs into IMSHO, is that it looks like this, where you have, sort of reasonably large coefficients at when the sort of basis function you plug in is, well, the base function you pull out, is j, is of lower order than the base function you pull in. But then as you go higher, it really decays away. And for an analytic map, it decays away exponentially fast. You can see that it sort of goes away like that. And the line there really depends on the rate of expansion, this gamma check rather. Right, and so we can actually show using these oscillatory integral techniques that the decay is, the decay off this line is in fact just the spectral rate of decay associated with the convergence rate of the map F. And in particular, I should probably say that the spectral convergence rate is just the number of derivatives that that F dash has. So it's these regularity conditions. So if it's analytic, if F is analytic on some Bernstein ellipse, or if the VI's are analytic on some Bernstein ellipse, then of parameter e to the delta, then this will decay as e to the minus delta j minus pk, which is, you can see this here. This is the Lanford map, and it really goes off quite quickly. The kind of, I guess, relevant, we're going to use these bounds for the validated numerics in various ways, but the sort of functional analytic upshot is that the transfer operator is kind of like an upper triangular matrix. So everything above this, oh no, okay, I got rid of this, is everything above the actual diagonal plus something of kind of pretty close to finite rank, which is everything below the diagonal, because it, like the coefficients just decay away really quickly. And so we're going to use this to prove convergence of a Galerkin projection method, which is essentially that we take some finite dimensional matrix. Right, we project onto some finite dimensional operator, which is obviously something we can represent on a computer. And in the matrix setting, that's going to be the top, n+1 by n+1 block of the matrix. But so theoretically, we'll represent this by projecting onto by using a projection, which will just be onto the first Chebyshev modes, and then restricting that to Chebyshev polynomials of degree n, so things that can be spanned by the first few Chebyshev, n+1 Chebyshev modes. And then, this is pretty standard. We just substitute this sort of finite dimensional operator for the actual thing in whatever problem we want to solve. For example, the invariant measure is the one eigenvalue, and we of course expect to get some that this rho n that we get using this projected version should converge to the true one. And it turns out, in practice, this works fine. We want to prove why it exists though, and we're going to use essentially this upper triangular idea, which is that this sort of, essentially we're going to turn our matrix, we're going to perturb our L transfer operator into a block upper triangular matrix by just getting rid of, in a sort of matrix format, we're just going to cut out this part of the matrix. And this top block here is going to be, is our finite dimensional projection that we can represent on a computer. And then the rest of this is just some stuff. But if we just do normal matrix functions on this, if you think about what you do, like if you square a triangular matrix or you take an inverse of it. The top left, this block here doesn't depend on anything that's going on there. So this is kind of acting by itself. I probably should just say why we don't get rid of the rest of it. Like just take out the rest of it. You can see here that the coefficients are quite big. And there's no way you can really function space, unless it's analytic, there's no function space you can really do much, like you can use to make these other bits small in norm, because your transfer operator is quasi-compact, which means it's not really actually compact. So that's why we have this kind of slightly dodgy approach, or slightly more complex approach. There are definitely other ways you can do it. But this is what we're going with. And you can show that because, essentially the bit you've taken out here is of such small norm, just by like adding up the norms of the coefficients of the matrix, you can show that this operator here, this L and twiddle, is very close to the full matrix, the full operator. And it is of this kind of, the difference depends on the spectral convergence rate, essentially, depending on this map N. And so that's how we can show that this matrix Ln, or this matrix L twiddle n, approximates the full transfer operator. But of course, we want to actually get out, like solve, linear algebraic problems with this transfer operator. And the way we're going to do that is, in fact, by constructing a different operator, which is just a matrix function, or say just a algebraic function of our original transfer operator L. And this, what's quite nice about this operator is that you can save it and just keep reusing it for different reasons. And so this operator is called the solution operator, we could call it that. And it's just because we're interested in the resolvent data at 1. It's just the resolvent of the transfer operator at 1, which of course is, singular, right? So we add a little rank 1 perturbation that involves the left eigenfunction at 1, which is total integral. If you think about it, you take a measure density and you push it forward, you're going to get another measure density. So the total integral, a probability density. So total integral is invariant under the action of this transfer operator. So this, so it turns out that this solution operator is, bounded and nice and everything. And if you feed this constant function, which we put in here, which you could make non-constant, but it's nice to have a constant, it will spit out the asim, the invariant measure. And if you apply S to a function which is in the kernel of this left eigenfunction, so a function of zero integral, you get out a sum of iterates of the transfer operator, which you may remember is something, it turns up in a bunch of things actually, but in particular it turns up in the diffusion coefficient as a sum, and that's where you get this 2s thing in this expression here, which is not a particularly transparent equation, but it is in fact what it is, and it's a very, it's just like some linear algebra. You just got to plug your thing in. So that's kind of what this solution operator gets us. It's quite nice to deal with theoretically, because it is just an operator function of this sort of rank 1 operator, really, whose we know everything about, because we know what the total integral of a Chebyshev polynomial is, and this is just a constant function, which is T0, the first Chebyshev polynomial. It's operator function of this and of L. And so if we define, again, this kind of twiddle, like this upper triangle, block upper triangular matrix, this is going to be very close in norm to the solution operator, the true solution operator. And furthermore, because you have this, again, this block upper triangular structure, the sort of top left block of the solution operator, this thing here, but for this matrix function, is going to just be the, it's just going to be the Galerkin projection and vice versa. So we can study a Galerkin approximation using, which I haven't really yet, a Galerkin approximation just by using this twiddle sort of trick, I guess. And again, we have this nice convergence. A corollary, I mean, an immediate corollary of this is that Galerkin approximations of the invariant measure will converge to the true ones. Yes, and again, the bounds, I should say, the bounds can be shown explicitly. You have a constant that depends on the on these distortion bounds, like the kind of a priori bounds on the regularity of your map. And then it will also depend on the norm of this solution operator, which is not, which is something which you can sort of play around and pull apart like this, the definition of it, and show that it really, what it really just depends on are sums of these L to the Ks on the kernel of the one left eigenfunction. These are quite well known in chaotic systems just for their own reasons, because they tell you essentially about how fast you lose information in your system. It's these idea of decay of correlations. And there are a priori bounds on this decay rate, which you can think about as saying, well, you get rid of the one eigenvalue in your transfer operator, which has got a spectral gap. Everything else is going to have sort of, you know, like the rest of the spectrum is in a ball of radius less than 1 in the complex plane. But yeah, these bounds are very, you get in the literature that people have shown are very weak. Like they're just they're exponentially weak in the sort of these distortion bounds. And in particular, like for the Lyapunov map, which as you saw is this very generic, boring, like fine map, if you try and work these a priori bounds through, you get sort of numbers that are like 10,000. And you know, it gets worse from there. Ideally, you would like to have something better, but it turns out that if you have, like when I was working through, we figure that if the map was analytic, you'll have exponential convergence anyway. So it doesn't matter if these bounds are really terrible. It'll just, you know, you just add a few extra basis functions and you'll crash through. But it is possible. And I mean, Isaiah has, and Stefano Galatolo and various other people have like sort of probed this. You can actually get quite nice bounds where you try and sort of establish a contraction in your Galerkin approximation, and then you use sort of the Soto-York inequalities, like various tricks of the trade to relate it to, well, not tricks of the trade, but like sort of standard theoretical concepts in chaotic systems to relate it to the actual full transfer operator like that, and you get quite good bounds, I believe. I didn't do that, but it would be very possible to do that. Right, so that's, I guess, the sort of theoretical idea of like how to establish convergence and how to bound the error in your approximation. But I mean, computationally, you've actually got to create these some sort of computer representation of this this ln, this finite rank operator. And I mean, well, we know it's just the first n+1 block of this transfer operator if you consider it as a matrix on Chebyshev coefficients. But the coefficients are, again, like they're integrals. How do you want to compute these integrals? Fortunately, I mean, it's because of the connections to fast Fourier, to Fourier series, you can essentially just use a fast Fourier transform, but you're not sampling from evenly spaced points. You have to sample from these so-called Chebyshev points. But yeah, you get the same kind of fast algorithm based on the Fourier transform that will spit out all the coefficients, all the J's for a given K. Like you just plug in LTK into these Chebyshev points, and you get a vector, and then you call FFT on the vector, and it's great and it's fine. Obviously, like that's a like estimating from a finite number of points, so you will get error. But there's actually some, a so-called aliasing formula, which is that the true coefficient LJK is just your the thing you got out of the fast Fourier transform on your finite number of points, minus a sum of some coefficients, of true coefficients of the LJK, which are higher order ones. but from the theorem before, we can actually bound these coefficients. So we can, I mean, if we're all doing this in sort of interval arithmetic, we'll have some interval estimate for L, M, J, K. And then we just widen our intervals by whatever the bounds for these are. And because these, you know, these coefficients decay exponentially as, you know, you increase M or whatever, you sort of go up in the sort of first index, that, like, you're not going to be widening it by much. With us, yeah, so we get this nice rigorous estimate for our matrices, which we can then go off and, you know, invert and do all sorts of other things with. Yeah, and it is quite efficient. So actually generating the matrix, you just have to do FFT on, well, it's an order n m squared log m, but m can be about equal to n. So that's quite quick, sort of in terms of complexity. When you actually compute this Sn, this solution operator, that's order n cubed, which is slow, and which, like, when actually doing the numerics, that took up, you know, like 95% of the time. Probably I could have used a better sort of algorithm to do that, but I didn't know what it was. So actually it could be a lot faster than that. But yeah, it's order n cubed, but it is reusable. So if you want to do a bunch of different stuff with the same system, you can do that, and you just stick a bunch of different things into the matrix. Say if you want to get invariant measures, we like create this matrix, and then we would just apply the matrix to the Chebyshev coefficients of constant function, and that would pop our invariant measure approximation. We could then go back to the sort of a priori work to estimate the BV error of the actual of the gap between the Galerkin approximation and the invariant measure. So they're actually, so the thing you get out are the coefficients, or rather sort of set of intervals, because we're working in interval arithmetic, containing the coefficients of this this Galerkin approximation, plus some bound between this approximation and the true value. Of course, you could roll the diameters of these intervals into the BV error as well, if you wanted to do it that way. So this is kind of like, I guess, so picture of what you do. Like in the theoretical world, you just apply the solution operators to a constant function, and you get out your asim. In the real world, you apply a sort of, I guess, a vector, interval arithmetic approximation, or like kind of sort of bound, whatever the word is, sort of net around your Galerkin approximation to the constant function, and you get some vector in which the thing is contained, the Galerkin approximation is contained, and then, like, theoretically, well, we can bound this amount, and so we're going to get a BV error out here. And then, so this is somehow contained in this plus this bound. If you want to do things like diffusion, like diffusion coefficients, it's the same idea, but just a bit more. You know, you have to multiply things, or maybe take intervals, and you'll get this kind of vector / interval, and then you'll also get a bound on yeah, sort of BV error bound. Although I suppose this here can in fact be, yeah, anyway. And then, yeah, if you sort of have to multiply, for example, by something where you don't have an exact answer for, so for example here where we're multiplying by rho, you sort of have to roll some of the error in. It's quite nice because BV is a and as are other things, but BV is a Banach algebra. Yeah, you multiply two things together and you just stick it in. Yeah, I mean, the only thing is that if you multiply, say, like rho n, which is a polynomial of degree n, and a, which is a polynomial of degree 2, you'll get a polynomial of degree n plus 2, so you've got to cut the rest off. I'm sure this is a sort of approach that's been done before. I'd be really interested if anyone knows, I mean, maybe we should talk about this later, but I'd be really interested if anyone knows like a sort of actual framework for doing this, or any numerics. I probably missed maybe in a talk about it that I wasn't there for. But it's effective. And so if we use, say, for example, 2048 basis functions, which took about 9 hours to run, the Lanford, right, we got, using the Lanford map, we can sort of get stuff out about the asymptote. I mean, there's some horrible long estimate of the coefficients of that, but if we just look at the Lyapunov exponent, which is the sort of dynamically important average over the asymptote, we can get, you know, 128 digits. And the same thing with the diffusion coefficient. If you wanted to do sort of higher order corrections, sort of Barry-S and stuff, you could get the same thing, and you just lose four decimal places every time because of your estimate on the solution operator. Yeah, so I guess the upshot of this is very effective. If you ever need this level of accuracy, then it's there. But if you also need like lower levels of accuracy or some sort of high regularity behavior, that I think is very attainable, is an upshot of that. It's just people like lots of decimal places, so I'm putting it in. In terms of things more things you can do with expanding maps, there are, well, okay, so Julius Lipanchuk and Oscar Bandler showed that actually it's not just the one eigenvalue, which this kind of approach is very geared towards, but you can actually show that all eigendata converge exponentially in a way that is sort of, you could make rigorous, or rather you could sort of make validated if you so wanted to. And in fact, Oscar and Anka Pol and some other people have been applying this to looking at the sort of Laplace spectra of some certain kinds of infinite hyperbolic surfaces. Like it's really, I mean, which has got, yeah, which sort of have relationships to, I mean, Selberg zeta functions, this kind of theory, and they get these really beautiful maps that are, it's very nice. And it's also possible to like apply this kind of ideas or sort of slightly related ideas, maybe more using Lasoda-York, different ways of sort of dealing with that projection to other things like rate functions for large deviations and so on. None of these, I don't, well, at least the first and the third one aren't necessarily, haven't like been rigorously validated, but the potential is out there if people wanted to do so, to make this kind of, yeah, sort of put it on a rigorous footing. But what I've been doing, I guess, sort of kind of extending on this, building on this, is looking at non-uniform expanding maps, which are maps which have some positive, so I mean, an example of this is the so-called Pomeau-Manneville system. These are like the other kinds of map, like the uniform expanding maps, except at one point their derivative is actually just equal to 1. It's not bounded above 1. The problem with them is that dynamically is that some stuff tends to get trapped around here. And this makes it, for various reasons, very difficult to numerically study, which is a bit of a shame because it sort of gets into the world of infinite ergodic theory, which is, I guess, yeah, something that one might like to have some numerics for. Ulam methods, for example, don't really work because they're very L1 based, and they don't have, yeah, anyway, there's lots of kind of interacting reasons why they're not very amenable to numerics. And so, I mean, no one's really got anything for like alpha bigger than about 0.6. But I guess a nice thing has been that the Chebyshev Galerkin methods can be brought to bear on it in a way that I will explain. We use this idea of an induced map to actually get it into the world of analytic and full branch uniform expanding maps. So an induced map is just like a return map to some set. It's nice. Again, I mean, you know, yeah, like derivative array from 1. Its main problem is that it has an infinite number of branches. You know, the branches you have to somehow would like to be able to compute without having to iterate through this fixed point. To solve the first part, where you have to iterate, there's a nice, you can show that there's this real analytic function, A, which lets you write your induced map, this return map, which we'll call F, as opposed to T, which is the other one, as a, basically just as a, you can write it in a closed form. And it turns out that there's also an asymptotic expansion here, which you can put explicit rigorous bounds on the error. So you can essentially, you know, implement A in integral arithmetic, which is pretty nice. And then, well, you need to generate, like, if we can get a transfer operator, then you can apply Chebyshev Galerkin methods and like get everything out that we could possibly want. You probably, you know, if you go back to the idea of a transfer operator, which is a sum over pre-images with a Jacobian term, and you sort of work through this definition, you see that it looks like this sum here, which is obviously quite foreboding and not very pleasant. And also, yeah, it's infinite. And in fact, it decays polynomially. But it turns out because it's like an analytic function in I, you can use Euler-Maclaurin formula, the Euler-Maclaurin formula, again, in a rigorous way to solve this. And I suppose I could say as a side note, you could also do this with the gas map if you wanted to use the Euler-Maclaurin formula to calculate it. Right, and you get out some numbers, and sometimes these numbers don't really look very close to any other simulations you could do because those simulations converge so slowly. But you do get out some pretty pictures for statistics of both the induced map and the non-uniformly expanding map. So these are the invariant measures, which turn out to be quite hard to normalize, where the sort of semi-transparent is what you get if you do Monte Carlo simulation. And the upshot again is that you get some very accurate bounds. In fact, perhaps more importantly, you get numerics that are even correct. So, for example, if you use 512 basis functions for your Galerkin method, you can prove that the return time to this nice inducing set for what is actually a singular case is, you know, you can get some number of digits that it would take, you know, many times, you know, an exponential of like the age of the universe to get if you were to do it any other way. So I suppose that's not particularly practical or a particular practical interest, but it does really let you understand things about infinite ergodic theory in a way that people have not been able to do in the past, which is cool and exciting. And hopefully, I mean, this maybe gives a blueprint for what you could do for some more complex systems as well with the inducing idea. But yeah, I suppose in kind of maybe what that illustrates is that these kinds of Chebyshev Galerkin discretizations are very effective at estimating statistical properties of these uniformly expanding maps. And that actually, and the sort of the power that they have lets you actually go on further to look at more complex problems, perhaps in various directions. With that, some ways that you could actually improve the method itself, or rather that you could, different ways you could go with sort of the actual, yeah, with improving the method rather than finding applications for it, are looking at sort of higher order function spaces in which you could sort of, you know, look at, say, response to perturbations, response of the measures to perturbations, which is, I guess, something that I do in other parts of my research. You could get these, like, apply, sort of modify these, use these, sorry, brain, get these a posteriori estimates on the decay of correlations that people like as I have been doing, but apply it to these Galerkin methods, as particularly also when you start to get to higher order, like higher regularity function spaces where we don't have theoretical results a priori for it. And you can, and maybe also like what would I think perhaps be harder, but would be quite worthwhile, perhaps, is modifying it to work on these methods to work on general spectral data in a way that is rigorously validated, which is not something that has been done as far as I know, though it may be happening. Yeah, that, and of course you can, you know, there's all sorts of things that you could apply them to, and I'd be very interested to hear about any, yeah, you may have. So.
Thank you very much. Well, thank you very much for your very nice talk and many ideas in there. Very impressive. Well, let's open the floor for questions. Just unmute yourself if you have a question and you can ask it.
So I have a question. Do you think, so if you were going to try to apply this to higher dimensional maps, say 2D instead of 1D, of course there's numerical, the numerics is harder, but are there also theoretical problems?
So if you're thinking about 2D maps, okay, so if they're expanding maps, I don't think there would be. You do, I mean, so if you couldn't use BV is one answer for that. They have trouble with that in high dimensions, but you could probably use a sort of Hilbert space and you'd have no trouble. If it was maps, yeah. If it were maps that were like expanding in one direction and contracting in another, yes, you probably could also do that, but then you'd be working in spaces of distributions, which you might have to think a bit harder about. I think it'd be fine. Yeah. Usually it's just cursor dimensionality. That's the only thing you get into.
Thanks.
Maybe I have a somewhat related question. So if you don't care about the accuracy so much, but more about the least number of modes you need to get the thing going, which maybe becomes the problem if you go to 2D, for instance. How much, I mean, how does this compare to the approach you mentioned in the beginning, which is the piecewise constant approximation?
Right, to get it going. Well, you would really, I think it would depend on the, like how sort of, how nice the map was, you know, so like the Lanford map's very nice because it's almost flat. If you sort of started to have wiggles, you would need, like, to resolve it, you would need to have enough basis functions. And so there, I think Lam would do, so which is the piece partition would probably do better because it has a lower overhead because it's a sparse method. So you can, you know, because it's just like blocks are just going into other blocks, you can sort of write that as a sparse matrix and it's sort of things are order n instead of order n squared or order n cubed. Where n is the number of basis functions. And so if you need a certain number of basis functions to resolve things, then you would you just have a lower overhead and you just like want to go a little bit over that number to resolve it to get something reasonable, then that would, yeah, then Nonlinear would work fine, yeah. Would be the better.
One question, but I think for your basis, for Chebyshev, do you need the map to be full branch? So no discontinuity coming from the fact that the map is not full branch, or are there workarounds?
Yeah. So yeah, you do need it. If it's got a if you have a Markov partition, you can just I mean you can just sort of chop your space up into a bunch of different domains, and then, you know, do Chebyshev on those ones, so they won't actually be you know, yeah, so you sort of like it's not everything is going to, like, bits of your domain are going to, like, bits of other ones. You have like a matrix of these transfer operator matrices, as it were, and so that works. If you don't have a Markov, if it's not Markov, then yeah, no, it doesn't work. You have these discontinuities where it'll still converge, but it'll converge slower, and you may as well just use all one because of the computational overhead. But you could try, like I've been trying stuff with, well, I haven't in the past fiddled around, but like stuff where you like just construct an induced map to a Markov state, and that seems to work quite well. But then I guess to be rigorous, you need to like bound the return time to this sort of inducing set.
Okay, Any other questions?
So maybe you mentioned that, but which kind of software did you use to get to do all your computations?
So I was using Julia, and I was using a well, I suppose the validated numerics package, which I think David Sanders, who was here at least, is sort of runs. I didn't actually use haven't written up a proper package to actually do the validated numerics, but you know, I've got the code. Yeah, that's
right. Yeah. I mean, it's good. I have some students using Julia right now with the interval arithmetic, and they're quite happy with that. Okay, thank you.
I think there was a question in the chat ages ago from Peter. Yeah, so the transfer operator is very nice in the uniform expanded case. In the general situation, you need to, I mean, really, it really depends on the map. If you can find a function space with in some sense high regularity, even if you have to sort of make it a sum of, do something a bit wacky with it, if you can find a function space that you can approximate very nicely, then this should all go through quite well. At least if you modify your function, modify your basis elements or something to make it so that they kind of fit nicely into that function space. Otherwise, you're kind of a bit on your own. I mean, it's just a theoretical thing. There's only a certain subset of maps that they can say anything about theoretically, and if you can't say anything about it theoretically, then you can't do numerics for it. Or you can't do rigorous numerics for it. You can do any sort of. Yeah.
Okay. Are there any other questions?
Can I ask something? Yeah.
Yes.
Yeah, I have a question about studying the convergence of the transfer operator by using the resultant operator S, right? So how does that compare, for example, to evaluating the spectrum and studying the stability of the spectrum of L? Studying the resultant operator S versus studying instead the stability of the eigenspectrum of L.
Yeah, I think they're very similar. The reason that you would study, so I mean, if you want to look at these kinds of diffusion maps, that is, you're just looking at the resolvent. You're trying to get out the projection of the resolvent. Study invariant measures. So I mean, Ulam tends to go more for the studying the stability of the spectrum, which is of course a more general idea. Yeah, it's 6 of one, half a dozen of the other. This, I think, just probably maybe I would, because people tend to do it more to in terms of stability of the spectrum. If I were to do this again, I'd probably do it in a spectrum way. But they're the same idea, really. Yeah.
Okay, thanks.
This leaves me to thank you again, Caroline, for this really nice talk, and thank you for staying up so late at night to enlighten us.